I think there could be a fair complaint about trigonometry that it's become somewhat irrelevant with technology. One of the things when we do the graphing sections, which are really difficult, is obviously technology now makes it so easy to understand to make the graph. So it's good to understand what's going on beneath the surface, but it'd be easy to just get on GeoGebra or Desmos or something like that to do those graphs for you. Well, we're about to enter a section here where there's a number of trigonometric identities that really have become outdated. I'm sure 100 years ago these were very useful tools, maybe even 50 years ago. But they've kind of lost their necessity here with the advent of technology. With that said, let me talk about what these formulas are about. We're going to be looking at the sum and difference formulas for both cosine and sine. And the idea behind them is that suppose you had an angle like 75 degrees. Now, we don't have this on our trig function. We are on our unit circle. We don't know the 75. But what we could do is play a little bit of a trick. We could turn cosine into two different functions, two different angles that we know. Couldn't I turn 75 into 45 plus 30? And then these are two angles that we have on our unit circle. So while I know nothing about this one, our unit circle doesn't help us, I do know something about 45 and 30. And I could then use these formulas that were derived many years ago, I'm sure, that help us see, okay, well, if you have the sum of two angles, you can prove the identity is proven that it's the cosine of the first, cosine of the second, minus the sine of the first, sine of the second. Now, these two angles, they are not in the same triangle. It isn't to say that these are, well, I should make this a right triangle. It isn't to say this is angle alpha and this is angle beta. It's not true. There are angles anywhere that we are trying to sum together to see what the ratio that they would create. And again, this was primarily a trick for if being able to turn an angle that we don't know anything about into the unit circle. Now, I would always give you a formula sheet for this, but notice the pattern here. If you're doing cosine, we'll see the opposite's going to be true with sine here. If we think we could add together two angles to take the cosine, then it's the cosine, cosine, sine, sine. Do you notice the pattern? And then it's the opposite. This is positive and this is, so we subtract. So cosine, cosine minus sine, sine. And then the negative, it's the opposite thing for subtraction. You could do the same trick as suppose we were trying to, so if we found that the angle we're looking for could be made up of the difference of two different angles, we could play the same game, but this time our formula would have a plus. Okay, so let's take a look at one here. So we have the difference of two angles. Now these are two angles that we could find on our unit circle. And so we could just use this identity. But if we subtracted them, they would not necessarily be something we know anything about. We'd have to get a common denominator here. It would be over 12, and that wouldn't be on our unit circle. But because we have that identity for the difference of the two angles, all we have to do is plug it into the formula. So this formula only requires things that we can find on the unit circle, which is then super helpful. Now, it is possible, if you think about this, that there are more than one way that we could create some kind of angle, but we'll see that later. Let me just keep going with this. So what we see here is cosine, cosine, sine, sine. First angle, second angle, first angle, second angle, and then it was a minus, so we're going to create a plus. Now, all we got to do is look these up on our unit circle. We get all of these values right here. Now we simplify. So do you remember how with square roots you multiply what's underneath the house? So we simplify this, got a common denominator, and this is going to be the best we could do. Okay, so let's do it again. We have the difference of two angles, and we know these angles. They're all on the unit circle. So we can do cosine of pi over 3, cosine of pi over 4. It's the opposite sign, sine of pi over 3, sine of pi over 4. Okay, so this is a 60-degree angle that is going to be 1/2. This is radical 2 over 2. So you can just read these off the unit circle. I'm trying to do all these by memory, so I hope I don't screw up. This is 60 So that is radical 3 over 2, and this is radical 2 over 2. Okay, making sure I'm right. 60, yeah, 3, yeah. Okay, now all we got to do is simplify. I get radical 2 over 4 plus radical 6 over 4. Let's put those all over that 4, and we get this. All right, now this is actually the one that I illustrated with at the beginning. They gave us an angle that we don't know. They say, hey, find this. Well, of course, nowadays you could just look it up on your calculator and you'd have it. But if you wanted to step back a generation or two and wanted to use an identity, what you could do is you could see that you could turn this into 45 and 30. So let's find it. That's the sum of two different angles. And now this is what I started saying on the other slide, and I should have done it here. There's times that you may be able to find this different ways. There might be two different ways that you could add them, or two different ways that you could subtract them, and you'll get an equivalent answer. If you may have some square roots that don't look the same, but if you crunched all the numbers out, you would get the same thing. Okay, so here we have a pretty straightforward 45 plus 30. These are both two angles on the unit circle we know. So we are adding them. So cosine, cosine minus sine, sine as our pattern. So we plug it in here. Just looking these all up on the unit circle, we get this. We simplify again, and here we go. Yeah, so yeah, they're pointing out what I was just saying. There are other ways we could have gotten there. So it turns out 135 and 60 could have, a difference could have gotten us there too, and we get an equivalent answer. Okay, so how about the cosine of 105? If you want to pause it, I'd recommend you try this. Again, there's multiple ways you do this. I'm going to look for the easiest way. Of course I am. I'm always looking for the easiest way. How about this? 60 plus 45. So our identity says we can do the two cosines. It's addition, so we get subtraction. Oh, I'm sorry, that's not right. And then we do sine, sine. Okay, you can read this off your circle, but we're just going to knock this out. 60 is 1/2. 45 is radical 2 over 2. Is this? I don't know if these are the same numbers we did already. Okay, sine of 60. Hold on, I got to make sure I'm doing this right. 30, 3, 2, 1. Yeah. 1, 2, 3. Yeah. Okay. Okay, so here we go. I've got my values. Now let's simplify. I've got radical 2 over 4 minus radical 6 over 4 all over 4. Now we're going to find, and again, I'll leave the proof to the textbook. I don't know if it would mean anything. I'm not sure off the top of my head how these are derived. I know it's in the book. We could look that up and prove that these identities are the same thing. But we have them just as we did for cosine, we have them for sine. So if we find two angles that we want to add, now notice the pattern here. The sign stays the same. If it was addition, it stays addition. And it's sine of the one, cosine of the other, cosine, so then it flips, cosine, sine. You following that? So again, I would give you the this on your formula sheet. I don't expect students to memorize all of these formulas, but again, there's the pattern. Sine, cosine on this. The sine stays the same, cosine, sine. Okay, let's take a look here. So notice again, what we have now is we have two, so this could have been the sine of 15 degrees. Well, I don't have that on my unit circle, but if you turn it into sine of 45 minus the sine of 30, or minus 30, these are two values that are on our unit circle. Okay, so let's crunch them. So we've got the difference of two angles with the sine. So it was sine cosine minus cosine sine. Just plugging those in. All right, we crunch this down, just getting all of these values off our unit circle. All right, here they are all in the formula. Multiply them and we get this. Okay, what was the second one? I don't even remember what it was. So 135 minus 120. Okay, two values that we can find on our unit circle. Just reading those off, they got them all there for us. Just reading them off of our unit circle. So remember, it was sine cosine minus cosine sine. Okay, we've got them all in there. Now let's just crunch. We get down to this. Yeah, I don't know why they wrote that the other way around. Not really necessary, but there we go. Okay, so that's all there is to it. So again, the point there is that we have found we have an angle that we can't find on the unit circle, but there's two other angles that would get the job done, two that we do know. So if we can pull that off and find it as the sum or difference, we could then use those cosine sine formulas. They're really pretty much plug and chug. Again, they're pretty irrelevant at this point, but there they are. Okay, now one final type of problem here where we're going to have some inverses inside of a sum or difference. So look what we've got here. We really have the sum of two angles, right? Isn't there some angle that has a cosine of 1/2? Isn't that what an inverse cosine is? There's some angle that has that 1/2. And there's some angle sine that has 3/5. Now they aren't in the same triangle. These are totally different angles. So here's what we want to do. We want to work these backwards, find what those angles are. We want to find the angle that has this cosine of 1/2. We want to find this angle that has the sine of 3/5. Once we have them, we can then use our sum of, well, in this case, the sum of a sine. So let's go ahead and get started with that. Now, whenever we have an inverse, there's multiple ways to do this. I'm going to think of this as a triangle. So I have an angle here. It's got a cosine of 1/2. So 1/2. Okay, so that's, I'm looking for this missing side b here. So I've got 1 squared plus b squared equals 2 squared. So 1 plus b squared equals 4. So b squared equals 3. So b is going to be the square root of 3. Now it's plus or minus here. So which one am I doing? The cosine. So let's talk about this cosine. So they just assumed here that they would both be positive, but let's talk through why this would be. Do you remember how we would do this? Cosine has to be in the first, or inverse cosine has to be in the first or second quadrant. That's what it has to spit out. So if we're in the first or second quadrant, and then we're taking a sine, which is what we'll be doing in just a minute, that would have to be positive. All the sines, all the y's are positive. So we're going positive here, and we're saying b is radical 3. My pen is not working. Where is it? Okay. b is radical 3. All right. Now, how about for sine? Let's do a triangle for this one. Again, it's not the same triangle. It's a different angle in a whole different location. So I've got this angle. I should be calling this beta here, and I should have called this alpha. Now, opposite over hypotenuse is 3/5. All right, so we could do the Pythagorean theorem to find this missing side. I remember there's a real common one. It's a 3, 4, 5. This is going to be 4. Now, if I square root it, it could be plus or minus 4. I'm not sure which it is. But again, so inverse sine has to be in either the first or the fourth quadrant. Okay, so I need then, we're going to take a sine of that, and that's going to force us, so we need a positive sign. It's going to force me to be in the first quadrant. So I'm going positive on both of these. Now, we're going to use these circles, so we've got sine. Let's finish our angles here. So I forget what I'm doing here. Okay. We're going to need, yeah, I'm with you. It took me a minute, sorry. We're going to need, in order to do this formula, I'm going to go to the alpha plus beta formula right here. So the formula for this is the sine of the alpha, cosine of the beta. It keeps the same sign, and then it switches cosine of the alpha, sine of the beta. Okay, so we have two angles, and we are going to do their sum. So here's my formula. So what I'm going to need to put into this equation are, I'm going to need the sine values for the alpha. That was this triangle. And I'm going to need the cosine value for the beta, which is off this triangle. So let's start reading it. Here's what I'm saying. So I'm on that first triangle, the alpha. What was the value of sine? Well, sine is opposite over hypotenuse, and that's radical 3 over 2. You see, we said b was radical 3. Now let's switch to our other triangle. What is the value of cosine in this triangle? That's adjacent over hypotenuse. That would be 4/5. Okay, now we're to the first triangle again. Cosine of alpha here is adjacent over hypotenuse. It'd be 1/2. You see, I'm just reading the definitions. Remember, cosine is adjacent over hypotenuse. Just reading off of this triangle. And then lastly, we're back to the beta triangle again. And we want the sine. That's the opposite over the hypotenuse. And that's 3/5. Okay, well, we've done it. All we've got to do now is simplify. This is 4 square root of 3 over 10 plus 3 over 10, which is 3 plus 4 square root of 3 all over 10. So what we've done here is we made two triangles. We had some inverse functions, so we made their triangles, completed them, and then that allowed us to find both the sine and cosine off of these triangles, fill it into our in this case, sum formula, and tidy it up, and we got it. Okay, that's all we have here. So again, I've kind of already summarized this, but so we are finding the sum or difference of angles that we know off the unit circle to try to help us with some that we might otherwise not be able to find.